it is amazing how blind one can be when making these videos. So I have of course again made a mistake here. So the point is that of course this one last pathway is not called R1 also, but R2. Alright, so here we have the diagrams of the pathways. Now we need to understand what we can get out of them and how they are useful. Our aim will be at the end to simplify the expression where we have path, where we have the nonlinear response function and the electric fields, into something that we can handle. You know, we have now an immense bunch of different terms in this part that concerns electric field. As we will show, there is really an immense number of terms, and there are also 4 terms, or actually 8 terms in this response function, and we have to somehow try to reduce the number of those terms. And one of the ways how to do that will be to introduce rotating wave approximation. We will find that among the electric fields contributions there are different phase factors that oscillate with these integration variables T1, T2 and T3, and the same is done by these pathways. They also oscillate with the transition frequencies, and so it happens that you have lots of terms that oscillate under the integral. Those things we will say, well, they will not contribute by anything, because when they will be integrated over some smooth field envelopes and so on, they will give us some very small contribution. But there will also be parts where the pathway phase factor will cancel with the phase factor from the fields, and those will be the big contributions. So we need to know what type of a phase factor one can expect from these response pathways, Liouville pathways. So let's take the R2 pathway, and using the diagram, actually let's write out how it's gonna look like approximately. So we will start with the initial ground state contribution. So this is the state of the ground state, and here is the equilibrium density matrix of the of the system. Well, actually let's draw this somewhere into the middle. We will need it more in the middle. So we will have the G, and this is the state of the bath, which is in equilibrium, and then we have an action of the transition dipole moment operator from the right. So this thing mu here will act and will transfer this G into E. So actually what will happen here, we will have the GE element here as the only acting, and here GE. This thing will show out the E. So if you look here now, you look here, well, let's take a different color. You look here and here, this should correspond to this and this. Yeah, now we see that here there is an action of the transition dipole moment operator again. That thing of course is an operator, but it has elements and so on. The only element that will be active will be the EG element, because it's gonna provide the G here for the scalar product, and it will show out the E. And again, this is the most out E, this is the most out E. They should correspond to these two. Now the action of the transition dipole operator from the right again, and that thing will promote, or will basically de-excite the thing from E to G. So it has to be again E, G, and here the element EG. So these are now just numbers. This one, these are numbers. So now we are in EG, and again I'm running out of colors. Again, this should correspond to this, and this. Now we have only the mu acting, and that one should be GE, because it should get us from E to G. Now we take a trace, and trace is sum over all states that we have, and obviously out of all this we can only have the n equal G contributing something. So when we sum up this, what we have written out here, should look like, well, we have all these numbers here. This is a number, this is a number, this is a number, and this is a number. So that's always EG, no, GE, EG, GE, EG. So it's GE, absolute value to the square, these two, and there are two more, so to the fourth. And here we have I guess we have well, what we have done, we of course forget to consider the time evolution of the system in between. But okay, we have at least found that there is a prefactor. In this case, there is a prefactor transition dipole moment to the fourth power. So alright, so let's recreate this again and not forget about the evolutions of the well, we can basically let just the system, not the bath, but just the system to evolve. So again, we started with G. Let's now also forget about about this part here. So the first one was the action from the right, so E, G, G, E, and now we should have U, T, U dagger T here. Well, if we have two-level system, this U should be well, U itself is e to the power of minus I divided by h bar Hamiltonian. If the Hamiltonian is diagonal, that thing looks like, you know, here you would have minus I h bar omega ground state T e to the power of minus h bar omega excited state T, and zeros on the diagonal. So it has only diagonal elements. We can write that here only the ground state element, this one, is contributing, and on the E side it has to be the excited state element. So we can write the E in here. Now yeah, and this thing continues. Then we have the action, let's say from the, let's have a look, from the other side. Okay, so we have the action from the right, so there should be from the left, so there should be EG, we have G, E in here, and there would be then the evolution in E, T, and on the other hand we changed nothing. There should be E, that was T1, and here there would be T2, and this we will continue with the, there will be one more interaction from the right, EG. So I will now write only what type of things will contribute when it comes to the evolution operators. It's clear that all other things will go will disappear in scalar products. So these G's or E's they are one. Okay, and the last thing is it's sealed again by the mu. So altogether, think of it hard, altogether the contribution would look like this, whatever we have found here, and there will be contributions, I forgot about the 3 here, depending on 3 times. So now these evolution operators, they are only these elements, so in a trivial case we can just write them out here in an order as they appear. T3, E, T2, then U, G, T1. Here we have U, E, T1, U, E, T2, and U, G, T3. Alright, all of these guys have their phase factors like here. So in fact what we have here is e to the power of minus I divided by h bar omega et3. Here we have also minus I h bar epsilon et2. Here it is minus I h bar epsilon g t1. Here it is plus I divided by h bar epsilon et1, and plus I divided by h bar epsilon e t2 plus I divided by h bar epsilon g t3. So let's see. So here is e2, so t2 e epsilon e, which can be cancelled with this one here. But then let's say t3 already cannot be cancelled, so we have to write minus I. Now we will use the omegas, the frequencies, eg, that's out of here and here, and they come with t3. And then there is this t1 contribution. Well, that's been here actually, this one. And then there is t1 contribution, which is this and this, and that has a different sign, plus omega eg t1. So this is the overall phase factor, omega eg t3 minus t1. That's the overall phase factor of the pathway R, whatever we have chosen up here. It's the pathway R2. So now it would not be so difficult for you to actually figure out what are the overall phase factors of all other pathways. Basically, the phase factor is given by whether the pathway is rephasing or not. So we have R3 and R2 with a phase factor which looks like this, T1, and we have R4 and R1 with the pathway that actually would look like this. You can verify that. So even if we would have taken into account evolution due to Bath degrees of freedom, this optical frequency, because that's the energy gap between E and G, would still be present there. This is a big optical frequency. So overall, even if there would be small differences, or if you, let's say, have more states, E and E dash or whatever, that would be not far away from each other, you could take some sort of an averaged frequency, which would be the average of all the EGs that you find there, that the pathways would have this type of phase factor, all of them. There is actually in a 3-level system one more possible phase factor, but that one we will only discuss a little bit later. It's not so important in here. So let's say this is some characteristic of the pathways of a 2-level system. We can extend that to the pathway of 2 band systems, and there is actually something. There's just a slight small complication if we extend this to a 3-level or 3-band system. So see you next, and see you at the next video.